רק מקפיאים תדר מסוים, כאילו נותן משקל לתדר מסוים. כאילו יש פה משהו לא חשובה. כן, אבל כאן את מדברת על משקולות שמקפיאות בתדר המסוים. מדברת על קומפוננט אחד
Okay, so good afternoon. We're continuing to discuss supervised learning, and the most simple network that we can think of is this architecture where we have a vector, well, it's almost the same, most simple, a vector of n inputs, and the computation that the network does is very simple. It's a simple linear sum, so y is equal to sum wi xi, and we're trying to teach this network to approximate a function by showing 8 examples. So the examples are x mu, y mu, and we have p of those, so mu goes from 1 to p. And we decided as an approach to teaching the network, meaning as an approach for choosing the weights w, to minimize the what we call the training error. So the training error so this will be our rule: minimize training error, e-training, which I defined as half sum over mu. Let's write it like this: y mu minus w transpose x mu squared. Okay, so this will be squared. Okay. Now, what I did last time is that I just took this expression, which is quadratic in the w's, and I rewrote it in a kind of a generic form for a quadratic function. So it's half w transpose phi w plus minus w transpose u, and I put here TR, which doesn't stand for transpose, it stands for training. Okay, plus A. And I just told you what are the values of this matrix, this vector, and this scalar, which is easy to do. So I leave it for you to check this. So C training ij is equal to 1 over p, sum over mu goes from 1 to p, xi mu, xj mu, and u transpose I is equal to 1 over p, sum over mu going from 1 to p, y mu x I mu, and A is this. Okay, so if we just look at this expression, this matrix and vector have a kind of an intuitive interpretation. This is the empirical correlation between index I and index j in the training value x. Remember that these are just drawn from some distribution. So I didn't mention this, but these are drawn IID. What is too small? IID from P of x. So in a sense, if we have many examples, when P goes to infinity, this becomes the correlation function of the indices of x. And this is but I'm calling it empirical because it's over the set of examples. And this is the empirical correlation between y, the desired output, and the index I of x. Okay, now, yes?
Okay, you talk about the error which is for a specific trial or the total error?
So, note here that we're summing over all the trials. And this is, of course, why we end up here with expressions that involve the sum over all the examples. Okay? So again, our approach is that we see a bunch of examples and we just try to minimize this error over the whole set of examples. And this is not the only possible learning rule, but this is the one that we apply. Well, it's what it is. It's the sum over the y squared. It's the variance of the y's in a sense, right? If the y's are zero, it's the mean of the y squared. I mean, it's the empirical measure of the mean of y squared to this half here. Okay, now one thing that I want to note before we continue is a property of this matrix C. So I claim that C is positive definite. And I want to show it explicitly. So one of the definitions of a positive definite matrix is that if we do a sandwich of, we take any vector U, this is an n by n matrix, so any n-dimensional vector, and calculate U transpose CU, this has to be a positive number for any vector. So let's check that. So for any U, U transpose C, U transpose CU, what is it? Let's write it down explicitly based on this expression. It's 1 over P, sum over I and J, Ui, now Xi mu, sum over mu, going from 1 to P, Xi mu, Xj mu, and all this is multiplied by Uj. But now you see that I have here actually, I can put this sum before this U, and then I have a sum Ui, Xi, Xj, Uj. So I'll also replace the order of this sum and this sum. And so what I will get is 1 over P sum over mu going from 1 to P, actually sum over I, Ui, Xi mu, and sum over J, Uj, Xj mu. Right? But this is nothing but the scalar product of the vector U with the example, with the x of the example mu. And it appears here twice, so it's just squared. So this is 1 over P, sum over mu going from 1 to P. The vector U dot x mu, let me write it like this, x transpose mu, U squared. Okay, so all these numbers are non-negative, right? Now, when we say positive definite, sometimes we mean positive definite, meaning strictly positive definite, meaning that this is strictly positive, or that it's larger than 0, or at least that it's non-negative. So clearly this is non-negative. Now the question is, can it be 0? So when is it 0? It's 0, so this is non-negative. And furthermore, it's 0 if and only if U is orthogonal to all the x mu, right, in our sample. So now let's think, so this leads us to a fundamental distinction in how we're going to treat the problem depending on the number of examples. If P is larger than N, then the generic situation is going to be that all these vectors x mu together span the whole space. So unless P of x has a very special structure, which we assume is not the case. If P of x has a very special structure, for example, suppose that P of x always chooses vectors within on some line or some plane, then we will never get vectors that span the whole space. But let's assume that that's not the case. If that's not the case, so the generic situation is that that with probability 1, essentially, once we choose n or more random vectors from this distribution, they will span the whole space, and therefore there will be no vector U other than 0 which is orthogonal to all of them. So in that case, it's strictly positive. So U transpose phi U is going to be larger than 0 for all mu. It's going to be larger than 0 for any nu, for any U. And what that means also is that the matrix C is invertible. It means that all the eigenvalues of the matrix C, so I remind you that this C is not only positive definite, it's also a symmetric matrix. Right? You can see here that if we exchange I and J, we get the same thing. So a positive definite matrix always can be diagonalized, and has real eigenvalues, and the fact that it's a symmetric matrix, it can always be diagonalized, has positive eigenvalues, and the fact that it's positive definite tells us that all the eigenvalues are positive, the determinant is positive, and this matrix is invertible. So in this case, C is invertible. The other possibility that I would like to discuss, and in fact this is true for P larger than N or equal to N, it's full rank. Now if P is smaller than N, then necessarily there are N minus P null vectors that are orthogonal to all the examples. Okay? We can always choose. If we have P examples, P is smaller than N, we can always find N minus P vectors which are orthogonal to all these P vectors. So in that case, there are vectors for which U transpose CU is 0. And that means that the matrix is not full rank. It means that the matrix is not invertible. Yeah, it is assuming it's assuming IID, and it's also in a sense a probabilistic statement, because of course you could choose. There is a possibility that you would choose the same vector twice from this distribution, but the measure of these events is 0. I mean, it's a probability in a sense. The probability that this will happen is 0. Okay. Okay. So. What we will do now is we will first discuss the case where P is large.
Just a second. Can there be a matrix, like can there be a matrix that is not positive definite that is invertible?
Yeah, but that's not, we don't, I mean, this matrix is positive, this matrix C is positive definite. The only possibility is that it might have eigenvalues which are 0, but all its eigenvalues are 0 or positive. And again, generically the situation is that if P is larger than N, all the eigenvalues will be positive, strictly positive, and if it's smaller than N, there will be some eigenvalues which are 0. Okay, so what I would like to discuss first is this case, P larger than N. And in fact, this was all kind of a sidetrack. We got these equations and I discussed the properties of C, but now what we want to do is to minimize this training error. So how do we minimize it? We take a derivative with respect to the elements of W, right? So first of all, before I even take the derivative, I want to discuss how does this quadratic function look like. So suppose that n was 1 in 1D, n equals 1, meaning that W is a scalar. The fact that C is positive means that we have here some positive coefficients times W squared, and it's a quadratic function. And so what we know is that it looks like this, right? And it has a minimum, right? In larger dimensions, in n dimensions, the fact that C is a positive definite matrix implies that if you would plot this function in n-dimensional space, it will be something like this. It will, again, have a minimum, a single minimum. And so we're really looking for this minimum.
Right now we're plotting the error function?
Yeah, we're plotting E-training. So this is E-training as a function of the elements of W, W1, W2, W3, okay? And this was a function of W. So this was a one-dimensional case where W is just a scalar, and this is a general case where W has n, there are n weights, and we're plotting the training error for a particular choice of x and y. For particular examples that we've seen, because this matrix is always positive definite, this function will have this structure, and it has a single minimum. And this is what we're looking for. But you can already see that the fact that C had a minimum, C is positive definite, is important, because if it wouldn't have, if it would not be positive definite, if C had some eigenvalues which are 0, then there will be some directions where this would be flat. So we would need to deal with that case separately. For now, it's non-flat. It's positive in any, it has positive curvature in any direction. Okay, so I think that I will actually erase this and keep this. So, okay, so we need to take the derivative of A training with respect to Wi and set it to 0. This is based on what I wrote here. So how do we take the derivative? So when we look at this expression is really a sum over I and j, Wi, C transpose, Wj. So C transpose, C training, Wi, C training, Wj, sum over I and j. So when we want to take the derivative with respect to Wi, we get two contributions, one from the Wi here, and one for the Wi here. So one contribution will look like this. Okay? Because essentially we have here the vector W multiplied by the vector CW. So the derivative with respect to the entry I here is the entry I here. But we also have the same expression coming from the from the place where I appears here. And in fact, this and this are the same number, because C is a symmetric matrix, right? Now, from here, what is the derivative with respect to Wi? It's U training I, and A doesn't play any role, and we're going to take the derivative. So we get here the matrix C training W minus the vector U I. And this is 0. So what you see from this is that if this vector is 0 as a vector, so let me just rewrite this like this. Because we know that C training is invertible, I can now write immediately that W will be C training minus 1 times U training. Okay, so this is the optimal solution. And one thing that I want you to note when you look at this is that this is actually everything that we've done is quite reminiscent of something that you've done previously in the course. I didn't do it on the whiteboard, but Neta did it with you, and this was dealing with an estimator for a linear estimator. Okay, so the rules of the game there were that you observe some x's, some vectors x's, and we call them then sometimes the firing rates of some neurons, and these had some probabilistic dependence on some parameter, and we wanted to estimate the parameter based on the values of these observations. But the equations that you ended up with were for a linear estimator were quite similar to these, and this shouldn't be too much of a surprise because we're dealing here with, I mean, the structure of the estimator, the computation that it did was exactly the same as the structure of a function approximator. But there are some conceptual differences. One is that here we're trying to approximate a function, right? Over there it was something a little bit different. We're trying to estimate some probabilistic, something that the x's were some probabilistic functions of some parameter. But if you think about what we've done there for an estimator, you can take the specific example where the observations are deterministically determined by the parameter. And then in a sense, it's the same problem as this one. What we're trying to approximate is the relationship between the observations and the parameter, okay? So in that sense, what we've done, what we're doing here is a specific case of what we've done there. But the other conceptual difference in what we're doing is that here we're learning from examples. Okay, we're not asking right now what is the best choice of the W so that over all possible instantiations of an example will do the best. We're right now we see some P examples and we're trying to do the best for these specific P examples. Of course, if P would go to infinity, then we would end up here not with the empirical correlation matrix and the empirical correlation between the desired output and the input, but with the statistical correlation, with the correlation matrix of the inputs and the correlation matrix of this output. And then we would be dealing with exactly the same problem that we dealt with when we discussed the linear estimator, again, under the case where the relationship between the parameter and the observations is deterministic. Right, but I'm saying, I mean, here it's explicitly deterministic. I mean, there's a deterministic relationship between X and Y this is what we want to approximate. Okay. Now, the other thing that
why is there is some W that is achieving zero?
I'm not talking now about the deterministic is not in the response of in what the estimator or the function approximator does. Our network is deterministic in both cases, but over there we had some observations, say some firing rates, and these firing rates were in themselves determined probabilistically from some parameter. So the firing rates were not determined by the parameter, but the probability distribution was determined by the parameter.
You define that
Here I'm...
a function of X,
Yeah.
not probabilistic.
No, exactly. Here there is some function of X, and this is what we're trying to approximate. Of course, one could generalize also to the case, and then it will be exactly the same problem. There's one other technical difference between what we've done, I think, what we've done when we discussed the linear estimator and what we've done here, and this is that when we discussed the linear estimator, we included also a bias term in the computation that the network does. So it was some WIXI plus some constant. When we allowed that constant to vary too, we could have done it here as well. So it's not a fundamental difference. Anyway, really the most important thing here that we're learning from examples, and we will want to discuss what happens now when we'll do it a bit later. We learn from the examples, from a P example, and we want to ask how well will we be doing over the larger set of inputs. Okay, but before we discuss it, so we have the solution for P smaller than n, larger than n, and now we need to discuss the case where P is smaller than n. Right? So we cannot do this. We certainly cannot do this because this matrix is not invertible. What does this mean? Okay, so let me first write it down. Rank So what does this mean? Does this mean that there's no solution to the problem? Exactly. So that's what it really means. What it really means is that there are multiple solutions to the problem, and moreover, as you will see in a moment, these solutions are solutions where we achieve zero error on all the examples. Okay? So if you just look at this function, this function, obviously, its minimum is somewhere above zero, because the error, by definition, okay, it's not written anymore, but the training error is a non-negative number by definition. So of course, the this minimum for an n larger than p lies above zero. But where p is when p is larger than n. But when p is smaller than n, as you'll see, first of all, there are multiple solutions. This function is a function of w, has some flat directions, and they all lie on the plane of this should be e-training. On the plane of e-training equals 0. Okay, so how do we show that? So actually, the way to show that is to see that explicitly that we can achieve zero error on all examples. And one way, and the way to do it is to just solve explicitly the requirement. Let's try to find a set of w's that achieve zero error, meaning that we try to solve explicitly the equation y mu equals w transpose x mu for mu going from 1 to p. Okay, so we have here p equations, right? We have n variables, and p is smaller than n, right? The number of equations is smaller than the number of equations, so it shouldn't be a surprise that we have multiple solutions. Now, I will write down how the solution looks like, and again, here I will skip some steps that I will leave for you as an exercise.
Can you just explain that picture over there, or both of those pictures? The minimum should be above 0, you said?
Yeah. So this was in that sense this was wrong, because this axis should be somewhere here. I just didn't think about it when I drew it. Okay, and the same is here. Obviously, this e-training cannot be negative. Okay, so now I erase it. Well, if our goal is to minimize the error, then that's the best we can do. Very good. Okay, so you're raising, I think you intuitively are thinking of a good question. If we can just trivially, if it's obvious that we can set the error to 0 on all the examples, maybe we're not learning a lot about how to generalize. So this is a good point. We'll come back to it. But for now, we're just seeing what this requirement implies for what we get. Yes?
So for p larger than n, we said that we can get 0 error?
No, so for p larger than n, I didn't write explicitly what is the error. You would need to, I didn't actually, it's a nice exercise to do it. But you can plug in this expression and see what is the error that, and use the expression that you get here to see what will be the training error. And it will be positive, it will not be 0, generally. Okay? And here I'm saying that the solution, indeed, I mean, there is a solution for which the training error is 0. Since we know that the training error cannot be less than 0, then this is the best solution we can find. And in fact, it's a family of solutions. Okay? So let's see that. Okay, so So as I mentioned, we just solve explicitly these equations, and the solution has the following structure. Before I write everything, I write it in a certain way. The optimal weights turn out to have the following structure. We can express them as a sum over some parameters omega mu times x mu. These parameters, I haven't yet specified what they are. I will in a moment. Okay, so I'll tell you what they are. So these are specified, but omega, yeah. Yes, omega. So because we're using W already, so omega. And plus another vector, which I will denote by W perpendicular. And let me explain what you see here. So you see that this part is really a linear combination over the x's of the examples with some weights. The weights will be determined. Okay? I will write an expression for them in a moment. This part is any vector which is orthogonal to all the examples. Okay, so and remember that because we have p examples and p is smaller than n, there are going to be n minus p. This is going to be, this vector spans an n minus p dimensional space. So we could write it in terms of n minus p coefficients that we can choose completely arbitrarily, each one of them multiplying one vector which is orthogonal to all these. So there is an n minus p dimensional subspace of choices that we can make, and this choice, this vector, does not affect at all the training error. Why doesn't it affect at all the training error? Because you can see that when we multiply this W with any one of the x mu's, here we'll get something. But this is orthogonal to all of them. So this part doesn't affect at all the output of our network on these p examples, right? Okay, so this is a very clear way to see immediately that there is a large range of possibilities for how we choose W that doesn't affect at all the output of our network. Okay, so this is the source of this part. And now what I need to tell you. So just to clarify what I mean here by orthogonal to all x mu's is that W transpose x mu is equal to 0 for all mu. Now what I need to tell you is what are the W mu's, or omega mu's. So the omega mu...
TR is training transpose?
And no, sorry. So, thank you. Transpose like this. Okay, so I need to tell you what are these omega mu, and so here I'm going to skip the details, but they have an interesting structure to them, so I will write it down and just discuss the structure. So it turns out that we can write the omega mu's as follows. We can write them as a sum over nu going from 1 to p. Q minus nu, q mu nu minus 1, y nu. So, in other words, omega as a vector is the matrix q minus 1 times the vector, I don't want to write it this way. It's not, okay, so this looks like a matrix multiplication of a matrix who is an inverse of the matrix Q, which I will write in a moment, times the vector Y, but now the vectors and matrices are in the space of the examples, right? This is not the indices going from 1 to n, right? So this is, Y is a scalar for each example, but there it's a vector living in another space, the space of examples. It's a p-dimensional vector here, and this is a p-dimensional matrix, which I didn't yet write. I will write it now. So Q mu, I will not write Q minus 1, I will write Q. So Q, which is a P by P matrix, is equal to X mu transpose X nu. again, I'm not showing this, but you will see this in an exercise or with Neta. And what I would like you to see is that there is a kind of a dual relation, a funny relationship, funny similarity between the solution that we got here when P was larger than n, where we inverted a matrix, an n by n matrix, times this vector, and the n by n matrix was kind of the correlation function, the empirical correlation function between the values of index I and index j of our examples. And here we're inverting a p by p matrix, right? And the p by p matrix, the new entry in this matrix, is the correlation between the vector x and the vector x mu and the vector x nu. It's a bit confusing, but I mean, these matrices are living in different spaces, right? This one is living in the space of indices of the vector, and this one is living in the space of the examples. The index is the example, but formally there is a similarity between the results that we got. I'll write it down more explicitly in a moment. Yes? Why you can't do further inverse? Yeah, you could do it. In a sense, I mean, you could. This is another way to treat this problem, to take into account the fact that the matrix has some null directions, and we'll get the same result. Okay. Okay. So just to note the similarity again. To note the similarity, maybe I'll write it. Okay, up to where can I write?
We should probably move to another board.
I should move to another board, okay.
Oh, yeah, like, yeah.
Below the square?
Yeah.
Okay, so I don't need a lot of space for this, so I will do it here. So note the similarity and the differences between the solutions that we got in both cases. In one case, we got the matrix Q mu nu, which is P by P, and whose entries are sum over I, xi mu, xi nu. And in the other case, we needed to invert a matrix C training, which is n by n, and whose elements ij are 1 over p sum over mu xi nu x j mu. Okay? So here we're summing over the index of the example, and we're looking at entries I and j. Here we're looking at entry I and summing over and looking at and summing over the entry for mu and u. So formally it's kind of similar but different. Okay. So anyway, this is a solution. This is a solution when p is smaller than n. And again, you see, just to sum up what we got. What we got is that we can always find a set of w's that will achieve zero error, which will perfectly approximate the function over the p examples. In fact, we have a large freedom in the weights to choose them in different ways, which all achieve this goal. So I would like to take a break.
אז אם היא באמת לינארית, אתה תמיד תוכל למצוא את הפתרון. בכל מקרה אחר, מה שיקרה זה שפי גדול ממנו, אנחנו לא יכולים למצוא פתרון מושלם.
אז כאילו, בעצם במקרים שיש מספר מאוד קטן, אני יכול להגיע לאפס, ברגע שהוא גדול, אז זה תלוי באמת מה איפה המקרה.
גדול וקטן, זה ממש חושב שגדול וקטן מבחינת מספר הדוגמאות, זה והפונקציונליטי של ה...
זה לא הביזנס דימנשן,
זה מאוד קשור לביזנס דימנשן.
כאילו הביזנס דימנשן זה בדיוק
זה הנקודה
שווה,
שאתה יכול...
אבל פה השווה אתה כבר אין לך את זה. כשפי שווה לאין, פה כבר אין לך בוודאות אפס, ושם יש לך, שם הביזנס דימנשן בדיוק.
לא, אתה שואל, זה משהו, זה לא בדיוק, זה לא הטרנינג ארור.
לא, שמה...
למה? יש לך דוגמאות, כמה אתה יכול לנתן?
אבל לא הנחת דברים ליניאריים. אז לא הנחת, ביזי דמנשן לא בהכרח זה משהו ליניארי. הנחנו שזה ריאליזציה. כן, ואז זה נכון, אבל זה כאילו, זה כמו...
אוקיי, בדיוק, נכון. אז הפט של הדוגמאות של ריאלייזבל.
כן. כאילו, אפשר לשאול משהו, למה במקרה עכשיו, למה במקרה שפי קטן אנחנו יכולים לבחור וקטורים אורתוגונליים?
כי בעצם מה שקורה זה שהעובדה שקיימים בכלל וקטורים שהם אורתוגונליים לכל ה-XU, היא תופעה של זה שפי הוא קטן יש לך מספר קטן של וקטורים, אתה יכול למצוא המרחב n-ממדי, יש לך רק פי וקטורים, אתה יכול למצוא n פחות פי וקטורים שהם אורתוגונליים. ברגע שיש לך יותר מפי דוגמאות XU, אתה לא תמצא וקטור, פשוט אין לך שום אופציה לבחור וקטור שאורתוגונלי.
כאילו זה CIJ.
למה?
כי הם יפרצו את המרחב,
שתי הוקטורים ולהפקיד אותה ולבחור על כל הדוגמאות.
כאילו פורסים סאב-ספייס.
ובשני אתה...
באמת הסאב-ספייס שלך זה היסטוריה של אורתוגונליים וכל ה...
צריך לכתוב את זה.
הבנתי.
שני...
לגבי הקטע הזה, המעבר הזה, כאילו, למה זה...
פה את צופמת...
כאילו, למה זה יכול, כאילו, מה...
פשוט צריך לעשות את זה, יש אלגברה שצריך לעשות כדי להגיע מהמשוואה שחשבתי שם, לפתרון הזה, ואני דילגתי על זה.
אוקיי. והפתרון הזה, כאילו, זה במרחב של CLP, זה במרחב הדוגמאות שלנו.
לא, הפתרון הוא בסופו של דבר כן, נכון, אתה צודק, זאת אומרת, ה-W הוא n-ממדי, אנחנו מבטאים אותו באמצעות וקטור p-ממדי, שזה האומגה, וזה הוקטור הזה. בעצם הוקטור הזה הוא נקבע חד משמעית על ידי הדוגמאות.
ואז יש לנו עוד n-p.
ויש לנו עוד n-p דקות חופש שאנחנו יכולים לשחק.
שאנחנו יכולים לשחק להם וכולם יהיו כאילו טובים.
נכון. כולם טובים באותה מידה מבחינת האירו, כולם ישיגו זירו אירו. עכשיו, יכול להיות לפעמים שאתה רוצה עוד, יש לך איזה... אתה רוצה שהמשקלות יהיו קטנות. אם אתה מוסיף איזה אילוץ, אתה רוצה שהמשקלות יהיו קטנות, באמת זה אומר שאתה רוצה יותר אילוץ.
אוקיי. תודה.
התרגום מהאומגה מה-P dimension וה-N dimension זה הדבר הזה, בעצם האומגה זה המקדם של כל אחד מהוקטורים מהדוגמאות. כל אחד מהאומגה הוא מכפיל את אחת מהדוגמאות וזה קובע את המשקלות כאילו משהו n-ממדי. ועוד אפשר להוסיף לזה משהו שהוא אורתוגונלי.
לא, שבמחשב זה לא כזה
Okay, so just one point that I was asked about, and I think it's worthwhile to clarify to everyone. So you see that these omegas are p-dimensional. The index is mu. So this is a p-dimensional vector, but it translates to an n-dimensional vector through this expression. So each one of the omegas multiplies an n-dimensional vector, which is in fact one of the examples, the x's of one of the examples, right? And this generates an n-dimensional vector. These omegas are determined uniquely by these equations. And then we still have the freedom, to add another n-dimensional vector which lives in an n minus p dimensional space, which exists because the number of examples is smaller than n. Because the number of examples is smaller than n, there exists an n minus p dimensional subspace of vectors which are orthogonal to all the examples. Once p becomes equal to n, the n examples fell in the whole space, and there is no vector which is orthogonal to all of them. And then this possibility, this ambiguity here, or this degeneracy, which is embodied in this part, it disappears. Okay, so now what I would like to do is to just mention a few important concepts. One of them is called the realizable patterns. So imagine that we have a particular function f of x that we're trying to approximate. So a set of patterns x mu, so a set of patterns x mu, or inputs x mu, which corresponds to some f of x mu, is called realizable if there exists, so realizable by our architecture. In our case, it's a linear architecture. If there exists W0, a set of weights such that the architecture exactly generates the right output for each one of the examples. In other words, y mu is equal to W transpose x mu is equal to f of x mu for all mu. So, or in other words, for these W's, the training error is 0, because the training error is 0 only if we exactly generate the correct output. So what you see this is just a definition, and in terms of this definition we can rephrase some of our results. We see that for P, the training error is the sum over the squares of differences over these examples, for that W. Yeah. So what we, just reformulating things that we saw, for P smaller than n, which patterns are realizable? All of them. Realizable. And for P larger than n, the generic case is that the training error is larger than 0, and therefore the pattern is not realizable.
Meaning none of the patterns are realizable?
Okay, so now there might be some special patterns which are realizable. But if we choose our pattern, we saw that if we choose our vectors randomly, then generally what we will get, there's no reason why it should be realizable, but we should have some reservations on the statement. So for example, note that if f of x mu, if the function that we're trying to approximate is a linear function, suppose that it is some w0, thank you. If it happens to be a linear function, then of course we couldn't find a set of weights that will realize all the patterns. It will be choosing the weights to be this w0, right? So it depends on the function. Therefore, we cannot make a sweeping statement about this. But typically, the situation is that the training error is larger than 0. By the way, it's worthwhile to go through the way we solve the problem for for p larger than n, where a priori it's not clear that we can see that the training error is 0, and see what happens when we deal with that problem. But if f is a linear function, and see that in fact approaching the problem by minimizing the training error does find a solution where the training error is 0 in that particular case. So this I will leave for you possibly as an exercise. Maybe we'll put it in one of the in the homeworks exercises. So in that case, choose w equal to w0 and all patterns realizable. But again, generally for a nonlinear function, the generic situation will be that when n is larger than p, when p is larger than n, we will not get. We choose some random inputs. We will not get a realizable pattern. Okay, now this is one concept that I wanted to mention, and another concept that I want to mention has to do with how do we now assess whether the network that we get from this approach, where we minimize the error over a set of examples, is doing well. So we need some measure of performance. And the measure of performance that we will look at is how well the network generalizes over an arbitrary choice of x, chosen from the same distribution from which we took the examples. So we're going to define the generalization error. Which is the average error of an arbitrary example. So the generalization error, which is a function of the weights, will be an integral over dx, p of x. This is a really n-dimensional integral, so maybe I'll write it like this, p of x, and the error of a network for that particular x with this particular choice of w. In our case, for the linear network, we can write what this is. There's a half. Okay, so it's the average of this expression over this expression over the distribution of the p of x. Now, if we would want to choose to search for, so what can we say about this generalization error? You see that the generalization error is a quadratic function of the W's. You see this here because everything here is quadratic in the W's. It's some quadratic form over the W's. And we could now discuss, and therefore it will probably have some minimum, right? I mean, it has to have a minimum. It cannot have a maximum. It's bounded below by 0, right? Generalization error cannot be smaller than 0. So it will have some minimum. And we could search for this minimum. Actually, we know what the answer will be because we've done that exercise. So because if we discuss the question of looking for the minimal training error, but take the number of examples to infinity, when we take the number of examples to infinity, we're really sampling from this probability distribution. And therefore, you know what the answer will be for the choice of W that will minimize the generalization error. It will be exactly the expressions that we wrote where instead of the empirical correlation matrices, the correlation matrices become the correlation matrices over the distribution of P of X. And in fact, you also saw these expressions when we discussed linear estimators. There too, we didn't look at a set of examples. We asked what is the best W over the distribution of the inputs. So there is some minimal, best possible generalization error. Maybe it's worthwhile to write explicitly how it's obtained. So so we can just deduce this from what we did for a set of finite examples, that the best minimal EG is obtained for some weight W star, and these weights okay. So EG tells us how well our architecture, our network, can approximate a function kind of over the whole set of examples, right? It's a global measure of how well it's doing. It is important to remember that it depends also on the choice on our assumptions on the distribution of the inputs. Okay, of course, if our inputs are always the same, as an extreme example, then of course we can find a good network because it's always the same. But or if the P of X are very narrowly distributed over a range in which our function is almost linear, then also we will do very well. But if our P of X is distributed over a large range over which our function is very nonlinear, then maybe we will not do as well. Yes?
I want to make sure that when you check generalization, isn't the idea that you train with certain examples and you test?
Yeah. So what I'm just, okay, so you're right. So maybe, I may think that when I'm writing this, I should clarify myself a bit more. So generalization error is really defined by the fact that you train your network on a certain set of weights, on a certain set of examples, and then you ask what is the error over a general set of examples. But note here that I'm writing it already as a function of the weights. So the weights were determined from some finite set of examples. But now if I'm looking at just as a function of the weights, I can forget about the fact that how I trained the network, and I can ask, what in general can this error be? And we could, without asking what was the training that we did on a finite set of examples, we could ask, well, how could we choose W so that this will be, I mean, obviously this thing has a minimum. It cannot be negative. So we can ask, what is the lowest value of this function that could be achieved? Yeah, of course, for a known f of x. Of course, yeah, of course. Suppose that you know that you knew f of x, you can ask, how could I choose W to minimize this expression? And this is what I meant when I wrote minimal EG. And this is obtained for a W star, which is really related to f of x and to the distribution of the inputs, in a way that I claim we know, because we can take the expressions for training error in the limit where the number of examples goes to infinity. And so I won't go through the details, but just a moment.
What does the X stand for? It's like W star?
It's a star. Now it's a star. Okay. So W star, I will just copy the expressions that we had for W, the optimal training W. W star is equal to C minus 1 U, where C is now not the empirical correlation matrix, but it's the actual correlation matrix of the input. So Cij is equal to 1 over to the average of xi, xj over the distribution P of x, and ui is equal to f of x xi over the distribution P of x. And so if you want to see why this is true, there are two avenues that you can take. One is to just explicitly start from this expression, rewrite it as a quadratic form over W, and minimize, and you'll get equations and expressions that are very similar to what we encountered when we treated the training error problem. The other way to do it is to take the results from the training error problem and just ask what happens. We had here there a matrix that I called C training and U training. What happens when n approaches to infinity? And when n approaches infinity, these become the empirical measurement of the correlation between xj approaches the true correlation function of xi and xj. When p goes to infinity, yeah, thank you. When p goes to infinity. All right, so now what I want to discuss qualitatively without proving is the concept of a learning curve and how performance depends on the number, the generalization error depends on the number of examples that were shown. So, so imagine that what we do is we do this exercise or game that I defined, where we show P examples and we train our network based on these P examples. Okay, and then we want to ask perhaps what is the generalization error of this network. So we show P examples, and here this axis will stand for an error, but I will consider two types of errors. So let's actually start, before we consider the generalization error, let's consider the training error. For the training error, what we saw is that when the number of examples is smaller than n, what is the training error? It's 0. So this is, maybe I'll use other colors.
This is not the generalized error.
No, this is the training error. So I'm starting from the training error. So the training error we know is 0 when p is smaller than n. And what will happen to the training error when p approaches infinity? And is this related to what we discussed here? Yeah, it becomes the best possible generalization error. When we see infinite number of examples, we're actually doing exactly this calculation. So if we will call let's call this the error that we've achieved for this W star, EG star. This is the best possible generalization error. If we perform our scheme of training over an infinite number of examples, we'll achieve an error which is this EG star. So let's denote EG star here. I'll actually do this with green because we'll use it in more than one context. So we can expect that the training error will start to increase and approach EG star. Now, one thing to consider about what I'm drawing here is that this by itself is a probabilistic statement. For each time I give you a set of n examples, you train some p examples. I show you some p examples. You train your network based on these p examples. You'll get a certain W. It will not be the same each time. And also the generalization error of that network will not be the same each time. So really what I'm drawing here is an average of the training error. Yeah, I'm showing an average of the training error over many times in which I train the network over p examples. So this is really what I'm showing. But when p goes to infinity, it approaches EG star. Now let's discuss the generalization error. So I will draw it I will draw it in red. And so again, we train our network using p examples. We get whatever W we get, and we ask what is the generalization error of that network. And now it's again, we average over instances of this exercise. So what happens when p goes to infinity to the generalization error? It approaches this quantity. But this time it goes from above. So if we show a smaller number of examples, the observation is that the generalization error cannot be, it has to go above, because the generalization error cannot be smaller than this quantity. So when we show an infinite set of examples, we're really finding the W which is optimal for this distribution P of X. If we show a bunch of smaller number of examples, we're optimizing our weights for these particular examples, but our choice will be not as good for a general W. So the curve goes like this. Now, how it exactly behaves here is not depends on many things. Depends on the structure of the function. It depends on the distribution of the x's. But we know that it has this monotonic dependence like this. And one other thing that we know is that beyond this point, it's ill-defined. The generalization error is ill-defined because when the number of examples is smaller than n, then we have multiple choices for W. And in general, they will not give the same generalization error. Okay. Then you have to decide how to average over them, and it might even, it's ill-defined. Okay, let's settle for that. Now, but what I do want to tell you is that there are interesting theorems about the behavior of the generalization error and the training error for large P. So, yes?
So this is all when you're training on P.
Yes?
On P examples, and then you're also testing on the P examples.
No, okay, so no. For the training error, you're testing on these P examples. For generalization error, you ask what would be this error, the error over a random example drawn from the distribution P of X. For that W.
So plotting both of the errors on the same graph is a little bit misleading then, because you're actually, you're testing this on different things.
Yeah, well, it's just two different graphs. It's two different things. That's why I'm using two different colors. Okay. It's two different things, but they are both errors. They have the same units, they have the same y-axis here, and they have the same x-axis. But they're two different things. One is the error on the data set of which we trained. The other one is the error over an arbitrary example. Okay. Now, what I just wanted to tell you is that it's possible to show that a training error as a function of P behaves like this EG star minus some constant over P when P approaches infinity. So this tells us somehow how fast we approach the training error approaches E.G. star when P goes to infinity. It goes like 1 over P. And more importantly, the generalization error also has this structure. And in fact, it also goes like A over P for large P. Okay, so this is the more important, interesting part. It tells us how as a quantification of our performance of a network, we're interested in the generalization error. And this tells us how the generalization error depends on the number of examples that we see. And it also goes like A over P, and interestingly, it's the same A that appears here and here. Okay, this is possible to show. And so just looking at these curves, we can just mention what are some of the interesting questions that we can ask about this problem, about learning from examples with this particular architecture and with the particular learning rule that we discussed. Because the learning rule that we discussed is minimize the training error over the examples. And so some of the questions that we can ask are, for example, what is E.G. for a given function? I mean, is it small or is it large, right? And for a given function, we might want to ask, can we achieve at all a representation using the linear network, which has sufficiently small error from our point of view? And another kind of question that we can ask is questions like this: how fast do we expect our learning to reach that error as a function of the number of examples that we see? So these are kind of generic questions that are interesting in the context of learning from examples. And the answers to these questions, of course, depend on various things. They depend on the function, they depend on the distribution of inputs, and they depend on the learning rule that we choose. Okay, so after discussing this example, I want to switch to another example, which is perhaps more important and plays an important role in thinking about neural networks as networks that perform computation. And this is the binary perceptron. I'll define it in a moment. Actually, I think that I forgot to mention when I started to discuss supervised learning, a bit about the context of why are we interested in supervised learning. So one reason, and the answer to this question, the answer to this question is true for everything that we've done in the course. Our primary interest is in learning something about how neural networks can perform computations. Okay, so therefore, the kind of we discuss networks with particular structure, usually linear networks, because we believe that this is the most simple description of what a neuron can do. Some of its inputs linearly, maybe do some nonlinearity over it, and then we want to ask how networks with particular structure can achieve some computation. Now the computation that we want to discuss is learning from examples. While we're doing it, we're also learning tools that are very important in many contexts outside of this general thinking. So for example, when we discussed the linear perceptron, which is a way to categorize examples, it's also a very useful approach for looking at data. And this is true also for PCA, ICA that we discussed previously. So again, the primary interest in this course is to understand something about what simple networks can do, but we're learning tools which are also often used in many contexts in dealing with data. All right. After I said that, let me define the linear perceptron. Binary, yeah, it's both binary and linear. You know what? Let me write a binary linear perceptron. It's binary perceptron and it's linear. Okay. So previously we discussed the architecture that we discussed was an architecture where we had an input vector, we linearly summed up the input with some weights, and that's it. That was our answer. So our network received as an input a continuous n-dimensional vector, and its output was a scalar, a number, continuous number. Now we will consider networks that receive inputs x1, x2, which are still linear. And what they do with them is they still sum them up with linear weights. Okay, so this is why this is linear. But the output that they spit out is just binary. It's a sign of W transpose X. Okay? So it's either -1 or 1, or you can translate it to 0 or 1 if you wish. It's a binary output. It has one of two values. So what can such networks approximate? These networks, we can use them to try to approximate a function, which is also a binary function of the inputs. And such functions are called dichotomies. So this network implements a function which is a dichotomy, right? If we take our space, x1, x2, x3, x4, for any given point in space, this function will be either 0 or 1, or -1 or 1. And but since the network has this simple structure of multiplying W by X and taking the sign, in fact, we can understand how this function looks like as follows. So imagine that this is the direction of W in space. And let's draw a hyperplane which is orthogonal to this. So this is a vector. So let's draw an n-1 dimensional hyperplane which is orthogonal to this vector. In this case, in the two-dimensional case, it's just a line. But if we were in 3 dimensions, this green line would be a two-dimensional plane. Okay, and in n dimensions, it's an n-1 dimensional hyperplane that goes through the origin and is perpendicular to this W. So in fact, what this network is doing is very simple. If we're on one side of the plane, W dot X is positive, and our answer is +1. And if we're on the other side of the plane, W dot X is negative, right? And our answer is -1. So what this network can implement, the dichotomies that this network can implement, have this simple structure that there is some hyperplane, n-1 dimensional hyperplane going through the origin, and the answer is 1 on one side and -1 on the other side. Okay, now, so this is probably the most simple structure of a dichotomy in n-dimensional space that we can think of, but it's also the prototypical calculation that a neuron does. A neuron takes its inputs, sums them up linearly, and then applies some non-linearity. And this is why this is how we think about neurons in this course. No, there are also non-linearities in the relationship between inputs and firing rate of a neuron.
Okay, there's just more layers.
Okay. So, so we want to kind of understand how good how rich is this structure in terms of what kind of functions it can, what kind of dichotomies it can implement. Now, if we ask something like how many dichotomies can be implemented by a binary perceptron, do you know what is the answer? How many different dichotomies can be implemented by a linear perceptron? infinite, because you can, every slight change in the W's will change the decision plane and will give you a different dichotomy, right? So there's an infinite number of dichotomies. So asking how many dichotomies can be implemented is not, this is not a very interesting question. So instead, what we will ask is something a bit different. What we will ask is, suppose that I define a certain set of points in the plane. So in general, if I choose p inputs, p points, how many different dichotomies can exist in general over these p inputs? 2 over p, right? 2 over p, because we can decide for each one of the inputs, different dichotomies over these inputs. So now we have a number, but not all of them can be realized by a linear, but maybe not all of them can be realized by a linear perceptron. Okay, so we can also ask how many of these can be realized by a linear perceptron. By a perceptron, you know what? Okay? So it turns out that the answer to this question is remarkably simple, in the sense that it doesn't depend almost on how we choose the points. And this is a special property of this problem. This is what I want to discuss. So it turns out that for almost any choice of the p points, the answer to this question is the same. And this will give us some sense of the power, the complexity or power of the linear perceptron in terms of how many of the possible dichotomies it can actually implement. Yeah.
Classifier has to be in the sheet of Zilling.
Yes. So in my formulation, in the way I defined it, yes, because here there was no bias term. We could have added a bias term, and in fact, as you will see in an exercise, once we understand the properties of this problem without a bias term, we very easily understand also how we can improve by adding a bias. Okay, so
you just choose one of the inputs.
in a sense, yeah, that's right. But I'm not going to do it for now. Just now, for simplicity, I will assume that there is no such bias, and therefore the decision plane goes through the origin. If we would add a bias, the decision plane could go through some other, doesn't have to go through the origin.
So can you maybe explain quickly how W transpose X looks visually? Like if I choose a particular...
what is W transpose X? It's the projection of the vector X over W. It's like for this particular, so in the two-dimensional plane, W transpose X is actually the distance. It's really the distance of this point from this plane, right? I mean, if you would. Oh well, yeah, but actually we don't care about the distance because we just care about the sign. So it's going to be positive if you're on this side, and it's going to be negative on this side, and this is what matters, right? It's like if you want to express X as the vector W plus a vector which is also orthogonal to W, this tells us how much of W there is in X. And in this case, it's a positive. We need to put in W with a positive coefficient, and when we're on the other side of the plane, we need to put in W with a negative coefficient. Okay, so as I mentioned, it turns out that the answer to this question is very generic. And I will start to discuss this now. I think I won't finish it today. But in order to discuss this question, I first need to introduce a concept called a general position. Because, as I mentioned to you, the answer to this question in principle might depend on the choice of the P inputs, right? So I will define a choice, positions, which is called the general position. So a set of x mu going from 1 to p, is in a general position and these are in n-dimensional space. So x mu vectors in n-dimensional space. If no subset of M smaller than n or equal to n of the vectors are dependent. This is the definition, and let's try to make sense of it. So let's make sense out of this definition. So first of all, if p is smaller than n, it just means that all these vectors are independent. Okay?
This is linear dependent.
Yeah. So sometimes this is called a linear general position, but I'll just call it general position. So yeah, and the vectors are linearly. Not statistically linear. This is the sense of linear algebra, that you can write one of these vectors as a combination of the other ones. This is what dependence means, that you can write the one of the vectors as a combination of the other ones. So first of all, if p is smaller than n, then it's basically this is just saying that all these vectors are independent. Okay? So general position just means that these vectors are independent. If I randomly choose p vectors on the plane, where p is smaller than n, I will, with probability 1, I will end up with vectors which are independent. Okay, you have to have a special coincidence that you choose this vector and another vector which is exactly on this line, and the probability for this to happen is 0. Now, if p is larger than n, it wouldn't make sense to use this definition, because any set of more than n vectors in n-dimensional space are dependent. So the requirement is now a bit weaker, and this is that for any subset of n vectors from the p vectors, these vectors will be independent. Okay? Yeah. So now suppose that so let's imagine two-dimensional space. Let's think of two-dimensional space. If I give you one vector, well, of course it will be independent. I mean, this is an independent set of vectors, so this is a general position. Now I give you another vector. As long as this other vector is not on the line going from the origin, these two vectors are independent, and this is a general position. Now I add another vector. So of course, any vector now that I will choose can be written as a linear combination of these two vectors. So this is not the requirement, not the requirement of the general position, but the requirement for the general position is that these two vectors together are independent, and these two vectors are independent. Now I'll add another vector. The requirement again is that any two vectors from this set are independent. Of course, if I choose three vectors from this set, they will be dependent because we are in two-dimensional space. Okay, now if we were in three-dimensional space, then the requirement would be that any three vectors from the set of vectors will be independent. Okay, so this is the concept of a general position. And now we reach a very important theorem, which I will write down, and we will discuss it next week. you know what, I need another definition before I write down. But so I will say it in words. I will just say what we're going to do. So now we can ask how many of the dichotomies on a set of points are realizable by a linear perceptron. And it turns out that the answer is the same for any set of points which are in a general position. As long as the points are in a general position, there is a formula for the number of dichotomies that can be realized. And we'll discuss Cover's theorem, which tells us what is the number of realizable dichotomies. Okay.
אליהם.
וגם תחת, כי זה לא האופי שלנו כאילו המקום הזה.
מה היית רוצה לשמוע את החש?
אנחנו פשוט נהיה פה 10 שנים. אז כאילו...
יפה.
נראה חירום רפואה וכל הרפואה של רופאים, ואני ריאלי, הוא בשבע. כן, 7 ל-10, לא איזה 7.
לא, אבל זה, מה אין לו... לא זה 7 שנים.
לא, אני קצת מפורט, מפורט לבד, זה שמאל, אני מתקבלה בלי כל רפואה. יש לו איזה טענה, רעיון שהוא... את הקליניקה הרבה 70, 7, זה לא יקרה. את מה שזה הוא לתת התמחות עם כל. זה ריאלי, וזה כאילו, וזה גם מאוד מאוד קשה להציג, אבל זה ריאלי. לא ככה מוביל. בקליניות לא פוסט והתמחות זה לא בעיה, כי אתה עושה התמחות נגיד
לא, אבל זה אנחנו יכולים לסגור גם במוצא שלך.
חוקר זה גם חוקר של חוקר וגם חוקר של חוקר. כאילו בסוף מה שאתה מתאר לפרט, יש רופאים חוקרים כמו חווי הדרמן שחוקרים שיום בשבוע.
לא, אבל שזה יהיה סיבוב הגיוני, זה לא איזה
בכלל רופאים, אז זה מחקר.
זה שאתה נסגור את זה, העיקר
זה לא שדחו את זה, אבל אתה לומד גם וגם.
לא, אבל אני יכולה שתי הבנות בלי האופן. היא נראה לי.
כן, לא, זה נראה לי הרעיון שאתה...
לא נראה לי,
בית חולים, לא רק בית חולים באופן.
הברית, זה שוק אחר. אנחנו לא יודעים בארץ שזה גם.